let me recapping briefly what I covered yesterday. So I introduced the filtering problem as having a signal which is denoted by X and is the hidden component, an observation process which is denoted by Y, which models the data, and the filtering problem deals with finding the conditional distribution of the signal at the current time, given all the observations accumulated from the initial time to up to the current time. And I gave you these pictures, which basically shows, is the whole picture. I have the signal in the state space R dx. I have an observation process in another state space R dy. Y, the observation, is going to be a function of the signal plus noise, and I make it specific on the next page what noise is. And we are interested in computing this distribution, this random distribution, which depends on the observation, and which I model, which I draw here some blobs to show that we want the distribution, not just one point, not just one estimate of the position of the signal, but if you want the estimate of the position of the signal, you can use, for example, the mean of that distribution, and that will give you what you want. Right. So I then introduced the framework, and the framework was introduced several times in terms of having this transition kernel KT, which gives you the transition from xt minus 1 to xt, and this was a particular example, the example, and I wrote down the kernel for you, and then I said that the observation process has the property that you can write down explicitly the law of yt given the position of xt, and I gave you again a simple example where I could write down explicitly what this density is. So again, this was the filtering problem, and I made the point, and I'm going to come back to this today, that the filtering problem evolves recursively. The conditional distribution of xt evolves recursively, and Ramon has covered it already. To go from pi t minus 1 to pi t, you go into steps. So first of all, you evolve pi t minus 1 by using the transition kernel, and you obtain something which is denoted by pt. So this is the prediction measure. This is the prediction step, and then you get pi t by multiplying pt with this by this function gt and normalizing, and then this is how you get pi t. And in terms of notation here, this transformation via the kernel. So if I have a measure, I put the kernel there. The measure with the kernel mu k is another measure which is defined for any Borel measurable set A. Mu k of A is the integral of k of x on A with respect to the measure mu. So that's the transformation. This is the first transformation here, written explicitly. You can write it explicitly in terms of the transition kernel. Okay. So I'm gonna just briefly say something generally about particle filters now. Well, I'm not going to cover this. I said a little bit. I gave a few details about what data assimilation is, just so that we see that the language is different, even though the problem is probably the same. And then this thing I didn't cover. So what are particle filters? So at this point in time, I'm not going to explicitly give you the description of particle filters. I'm just going to tell you sort of the general picture. After I give my talk, Elaine is going to come in, and she's going to give you specific and practical details of how you construct a particle filter. From what she told me, she's going to show you, she's going to give you details of the first step in the particle filter, and she's also going to say something about the second step. But I'm going to come back tomorrow and flesh in on the particle filters from the theoretical side. But you know, the big picture is that particle filters are algorithms that produce approximations of those pi t, approximation of those blobs that you saw there, and this approximation have a specific format. They look like this. They are measures. They are discrete measures, linear combinations of Dirac measures. So this notation delta with the vi is a Dirac delta distribution. Delta of x is a Dirac delta distribution at x. Okay, so you have the definition of there, and sort of the picture that you should have in mind is that this measure is simply the empirical distribution associated with a cloud of particles. So I have particles there. They evolve in my space, and they each carry some masses, alpha 1, alpha 2, and so on. Now, the important thing here is that these algorithms are recursive. So this isn't, you know, in the same class as an MCMC methodology. Basically, what this means, it means that once you got the approximation for pi t, you just need to use this approximation and the next set of observation, maybe just the next observation, to deduce, to construct the approximation for pi t plus 1. That means you never have to go back to, the beginning. You never have to reuse the information gained from the first t observations. Okay, so you know, the approximation for pi t does its best to exploit these observations. We trust it. To go to the next step, you just use yt plus 1. Okay, so particular cases of that is when all the particles have the same mass, 1 over n. It may be that the number of particles varies. This is unusual. The norm is that the number of particles is actually constant, fixed throughout your approximation period and is equal to, say, n, so that I have a probability measure. There are advantages to having random number of particles, but I'm afraid I don't have time to go into this. So this is just the big picture for this, and the generic particle filter, the generic sequential Monte Carlo method, as you will see from Elaine Stock, involves a sampling from the prior distribution of the signal, and then using a resampling technique from the weighted distribution of the approximation of the prior distribution. And I'm going to come back to this. There are some papers here, and I'm going to come back to the literature on this tomorrow at the end of the course. Okay, so now I'm going to slow down, and so this is the last page that I put up yesterday, and I wanted to make the point that data assimilation and filtering, they come together when especially in terms of the numerical approximations of what they want to achieve through numerical approximations. So what I put in here, here is, you know, sort of in this part on the left-hand side, I have a description. General description of a particle approximation. So what it involves, what a particle approximation involves, and then on the right-hand side, I have a general description of an ensemble-based algorithm, one that is quite popular in data assimilation. So this is just to show that basically there is a strong parallel between the two algorithms, and then on the next page you will see that the point that I'll make is that what you see on the right-hand side is in fact a particle filter. So on the left-hand side, what we have here, so a particle approximation, a generic particle filter, really sort of the most basic particle filter, really what it does, it starts with the approximation at time t, and then it follows the model, and the first step is called sometimes the mutation step, it follows the model to predict the this conditional distribution at time t. So it produces an intermediate approximation, and then it uses all the information accumulated between t and t plus delta. Here I want to make the point. Here I want to make the point that you may not need to apply this correction, this selection procedure all the time. You may not need to use to resample every time you get a new observation process. You may want to wait, right? Maybe wait to accumulate several observations, and then you apply this resampling procedure. You apply this correction procedure to get the approximation of the conditional distribution of the signal at time t plus delta. Okay, so throughout here, I have the superscript capital N to show that we work with capital N particles. Now in the case of ensemble, so this is popular with the data assimilation community. So here we work with a sum, a linear combination of Gaussian distributions. Okay, so again, so what do we do with them? They approximate the distribution at time t. You use the model. You produce a forecast. The first step is called forecasting that data assimilation as opposed to mutation, and you produce a new probability measure, and then you should be analysis. You have the analysis step here where you use the observation you incorporate the observation to produce the approximation at time t plus delta. Okay, so you can see there's parallel between the two, and the thing that I want to draw upon is that when you write your algorithms, when you write your computer program, basically what do you have to make a record of? So in the case of the particle approximation, you have to make a record of the weight of the particles and the position of the particles, right? So this is, there's going to be n vectors, each of them having d plus 1 dimensions, where d is the dimension of the state space. For the Gaussian approximation, you'll still have n vectors, but the vectors will have to have the weight of each element of the ensemble, could be the same weight, the mean of your Gaussian, and the covariance matrix. Now, of course, in the case of 3D VAR, this may be the same, so maybe you may not need this, but in general, again, you have here you make a record of your element of the Gaussian approximation by using this vector, which now has d squared plus d plus 1 dimension, or even less, because some of these matrices, the matrices may be, well, they don't have to be symmetric, but anyway. So essentially, the approximation, the posterior is approximated by this. In the case of particle approximations, the sum, the linear combination of Dirac measures, and in the case of the Gaussian approximation, by the linear combination of the normal approximations, of the normal, of the Gaussian random variables. Okay, the point is, in both cases, what I store these vectors. You can think of this as being modeling, we can think of this as being, sort of the position of n stochastic processes having values in some large space, right? Having values in some large space.
The n is the same on the right.
Yeah. So well, it doesn't have to be the same n. Typically in data assimilation.
No, the n inside the sum is the same n that you're summing.
It's normal.
Sorry, this is normal. I beg your pardon. Bad notation. I don't know how to. I mean, I should put. I don't know. What should I put in there? Yeah. So these are normal. This means just a normal with this mean vector. And, yeah. Right. So the way one can think of it, and this is what you can think of it as this what you make a record of as being. Go on.
How do you choose this omegas or the variances?
The variances.
The normal
Here. That's an excellent question. And I have an answer for you, but can I tell you the answer over dinner or something? You know, there are ways to do that, and you know, 3D vars keeps them fixed, and sort of there's hand waving. 4D vars has some ideas. We have some other ideas. So what we did, we designed an algorithm where sorry, the question was, what was the question? Yeah. So how do you choose the covariance matrix? So we have just come up with a paper where we show rigorously what the evolution of this W should be in order to obtain an algorithm which is rigorously justified. Right? So what we did, we said, okay, so how can we approximate, how can we develop? So you know, we know what 3D var does, we know what 4D var does, but there is no kind of algorithm, no theorem to show that as you increase the number of particles, the number of, not particles, the amount of Gaussians, you get convergence. So we started from that premise, and we found out that if you know this, you can construct this. You can have an evolution equation for the covariance matrix, so that you have this property, and you know it's there. We did numerics, and surprise, surprise, it turns out that when you do numerics, this performs better than the particle approximation. So the data assimilation people seem to be right in the sense that it's probably a better idea to use Gaussian approximation, but in fact, what they do, they just do particle approximations. Yes, yes. So this is something that it's meant to model everything that is used in data assimilation, as long as it's an ensemble based. Because you know, if you just have one, you know, you can just have one of them, one Kalman, you know, the extending Kalman filter. You can think of it as just one particle, but you know, it doesn't make sense. Go on.
I also see that one like an ensemble Kalman filter, except for the fact that it's not clear how. So the difference between an ensemble based and scheme and another would be rather than extrapolated. But my point is it clear that in a linear system, the convergence to the covariance given by the Kalman solution when the ensemble increase is true?
No. Yeah.
For linear systems, we know already that the ensemble Kalman filter when the size of the ensemble tends to fit this solution for the covariance are the same.
Yeah. Yes. Yeah. Yeah. So we have a recent result which says, suppose I want I want to approximate pi t with a linear combination of Gaussians, and there's some, I'm imposing the condition that the rate of convergence should be the optimal one, and out of that, what comes out of that in continuous time is that I tell you what the equation for A should be, what the equation for the evolution of V should be, and what the equation for the covariance matrix should be. It's not going to be, I'm not allowing you to use anything else. I'm telling you what you should use if you want the optimal convergence rate. Okay? So it could be that you can have something else which will still converge. That's not a problem. But if you want the optimal one, then you get that. But this isn't the point here. The point that I want to make is that if you are working with ensemble-based algorithm, you are still doing particle filtering. So you shouldn't be afraid of the word particle filtering. Okay? Yeah, so the way I see it, an ensemble method is a particle filter. So you cannot say that the particle filter is better than other particle filters. So within the class of particle filters, some are better than the others.
If you distinguish these as two,
right.
you're having left and right,
right.
different procedures. And somehow, these give as good a result, or even better result,
and that's exactly what we find out in our paper. That's exactly what we found out in our paper. And the reason for that is that this has more information in it. And it appears that is the right way to go, right? I'm not gonna say more about this. So what is the information? The information is in the tail. This one has no tail. which is bad, because if I want a good approximation, you know, we are all used to the strong law of large numbers. We are all used to the central limit theorem, which just tells us what happens in the middle. But I still need to know what happens in the tail if I want to have a good approximation. This tells me nothing about the tail. I mean, this is designed to stay there where the blob is. This puts the tail. There's the tail there. The normal is there. Yes, it's not a big norm. It's not a big contribution, but it's there. And that may be the reason why this does better. But anyway.
So now I have a question, but it's not really for you, but to the actual data assimilation people, right? I thought that one of the reasons people use ensemble common filters is because they don't want to store the covariance matrix because it's too computationally intensive. Is that correct?
It's one additional reason. The reason why they are being introduced a conceit because we wanted to have a flow-dependent error covariance matrix. It turns out that we also have the advantage of dimension, which is very important, which is the fact that we store a matrix of dimension of the ensemble member, not longer dimensional scale. But it's not being very.
But this is the anti-extended common, the anti-ensemble common filter, because here you don't only store a covariance matrix, you store one covariance matrix per particle.
Oh, wait. So, I mean, they'll tell you more than this. I mean, when I update this, it could be that I put all the covariance matrices together. I get one covariance matrix. I update that covariance matrix, and then I split them up.
You have some flexibility.
Yeah. So in fact, you know, when I represent this, I represent it by different covariance matrices. When I update it, it's going to be just one.
Okay.
But they have these huge models. You know, the model is just one that you work with on the higher. You know, this. No, I'm not going to go into this. Okay, but this is the picture. So that's what I'm saying. I'm saying that basically from the left or on the right, all I do, I look at particles. They may take values. They may evolve in a large space, right? But they are still particles. And the amazing thing about this, but once you accept this, so that we can call them generalized particle filters. If you just don't want to work with particle filters, any method that is out there can be thought of in the same way. There is nothing else but these records of stochastic processes, and you just think of them as the evolution of particles. So the same thing happens with classical particle filters, Gaussian approximation, wavelets, and Griffness. All of them are particles. You know, all of them, you just make a record of, you know, you have vectors in there, and you just think of vectors as being particles. Okay, so this is how you do the record of these particles. But then the next question is, you know, how do you approximate the error? And this is where you begin to, you know, you have to separate them, because for some of them, and in most cases in data assimilation, all I care about is I care about the difference between the conditional mean and the approximating conditional mean. And then I left it in there. But maybe you want to be, you want to be more. You want to do more. You can use the norm that Ramon showed you earlier today, right? Or you can look at total variation. So there are various norms in infinite dimensional space. There are various norms that you can look at, and as a result, some elements of this class may be better than others, depending on the choice of the norm. So up until here, I just wanted to make the point that data assimilations and filtering, Gaussian approximations or classical particle filters are one and the same things. The only difference is that you evolve in different spaces. Okay, so I just want you, so for those of you that work in continuous time, I'm just going to flash this picture. This is an example of a filter, which is called the Benesch filter, which has an explicit solution. So this is a nonlinear filter that has an explicit solution. And this is an excellent benchmark. If you come up with an algorithm that you think is going to work, you may want to test it on the Benesch filter. I wanted to put it there because I just wanted to show you how a particle filter looks like. And I hope I'm going to be able to find it. This is not the BBC that I want. So, let's see. I think I lost it, so I have to go here. So the model for this, I'm running now a toy example. It's a one-dimensional particle filter for the Banach filter. If you don't know what the Banach filter is, it doesn't matter. It's some nonlinear filter that has an explicit solution, and it allows me to show you that the particle filter works. So my initial condition of the signal is 0, right? So I let my signal evolve. So my signal solves. It's a stochastic. It's a Markov process, right? And it evolves randomly in time. Now I'm going to start the simulation. Now, so for the moment, the signal is positioned at this point where the triangle is. So that's my signal. So after oscillating a little bit at the beginning, the signal tends to go towards the positive part. Okay. Now what are the curves in here? The blue one is the prior distribution. So in this particular case, I can compute the prior distribution explicitly. This is the distribution of the signal, full stop. Right? So no observations. This is just explicitly the distribution of the signal. So in this particular case, the distribution of the signal is a sum of two Gaussians. So prior distribution is a sum of two Gaussians. So a priori, my signal will go either to the left or to the right. Right? I don't know where it goes, either to the left or to the right. And ideally, I should use my observation to find out where the signal is. In particular, I would like to use my signal to find out if the signal goes to the left and to the right. Now, the green thing is the explicit posterior. The green thing is the explicit posterior. In this particular case, I can explicitly compute the posterior, right? And you don't see it here, but the posterior is made out of again, of a sum of two Gaussians, but one of them is very, very flat. There's nothing there. There's no mass in there, right? But it's there. It's there, and there was something at the beginning, but gradually, as I get more and more observations, I realize the perfect filter realizes that my signal is not in there. It must be in here, and then I get a very steep Gaussian in here, and one which is almost flat in there. So that's the perfect thing. And then comes the particles. What are the particles? The particles, for each of the particles, I have a vertical line in here. So each of the particles in the cloud, in my cloud, is drawn here as a vertical line. So initially I have lots and lots of particles. They spread evenly, right? The particles spread evenly. I don't have many observations at the beginning, so I don't know. They just go in the direction that the prior tells them to go. And then gradually what happens, I begin to use my observation. I begin to use my observation, and what will happen is all the particles that are in the wrong place are going to be killed. And Elaine is going to tell you how the particles are killed. I'm going to tell you, I'm going to repeat that tomorrow. So eventually all the particles home in to the right-hand side, and then what you can do, you can construct the empirical histogram based on the cloud, and you have an approximation of the entire posterior. So you use those particles to get an approximation, not just of the position. That's fine. If you want just the position, you just get the average position of the particles and you find that out. You can get an approximation of the entire posterior, and this is pretty good. Okay? So this is how a particle filter works, and I'm going to come back tomorrow and I'm going to tell you the algorithm, but Elaine is going to show you details today about the numerics as well, about the statistics of it. But the point that I want to show you is, the point that I want to emphasize is that the cloud of particle not only is useful to approximate the position of the signal, that's fine. You can get everything. You can get an approximation of the entire posterior distribution, right? So if you want quartiles and so on, you can get them. Very useful for data assimilation. Okay, so I'm going to stop here, if I can. And I'm going to go back to, so, yeah.
Just for clarification, the prior is also getting updated there.
Yes, the prior evolves. I mean, it's a Markov chain. So the Markov chain evolves. Yeah. I have evolution of the prior as well, and I can explicitly compute it in this case. Okay, so now basically this is where I was supposed to be 35 minutes ago. But there you are. So the point that I want to get to is to show you this theorem, which is more or less framework independent, in the hope that people in data assimilation will pick it up and will say, okay, let's see if we can satisfy the condition of this theorem. Let's see if we can get a theoretical validation of our data assimilation algorithm. So I'm going back to the framework, and of course by now this has been covered already. So just to remind you, X is a Markov chain. Is given the transition kernel is given by KT. That's the notation for this. So this transition kernel, for fixed X, this is a probability measure, and for fixed A, this is a measurable function. This is the definition of a transition kernel. And the first thing that I need to tell you is notation. The prior distribution is denoted by QT. So this is just the distribution of the signal. No observations there. So I'm denoted by QT. The law of the signal, QT of A, is the probability that X time t is in the set A. So then you can take, so what is the connection between the QT and the transition kernel? It's fairly easy to deduce that we have, well, it should be the other way around. QT is QT minus 1 translated with KT, composed with KT. And what I did in here, so you can do induction, and you can show that, well, this is T. QT is the composition of all this transition kernel applied to the initial condition applied to Q0. Okay, so this is a very compact way to show the evolution of the prior. Now, what I did in here, I had to spend 6 hours in Dubai, so I thought, what better way to spend 6 hours in Dubai but to just write explicitly for our toy example, which is given by this, to write explicitly what QT of A is. And is this. And is nasty. And is bad. And it's impossible to grasp. If you look at this, so remember B, this is nonlinear. So you look at this. So it's impossible to say anything about this. It's impossible to draw any inference about this because, everything here is nonlinear. We don't deal with Gaussians, remember here. There's no Gaussians, right? So this B here is nonlinear. Okay? So that's QT of A, but the nice thing is that you can use the transition kernel and you write this long formula. You can write this long formula like this, or by using this recursive method, this recurrent formulation. Okay? So that's QT, and I'm writing here some of the properties of QT and KT. The important thing is there's this property. This is just a Fubini argument. So if you take QT minus 1 and amend it with KT and integrate the test function with respect to this, right? This is the same thing. This is an immediate application of Fubini's theorem. You take phi, you integrate with respect to KT, you get a function, which in turn you integrate with respect to QT minus 1. So in some sense, these two guys commute. You either update the measure, and then you take the test function and integrate with respect to the updated measure, or you modify your test function and you integrate QT minus 1 with respect to the modified test function, you get the same thing. Okay? Now this is going to come useful in the proof of the theorem, so do try to remember this. Okay, so YT satisfies this. I made this point already, and the property that I want to that we will assume is that it's a function of the signal plus noise, and we assume that the noise here, all these random variables are IID. They don't have to be IID. I just want to make my life easy. Mutually independent with laws which are absolutely continuous with respect to the Lebesgue measure on R. And this is denoted by GT. And again, the example here is YT is a function of XT plus a normal random variable. So again, what I did in here, I put together the law of yt up to y0 and xt up to x0. So I put together all these laws, right? And again, I get a long expression here, a long expression for this law, okay? Very complicated. It looks like it's explicit, but there's nothing you can say about it. There's nothing that you can say about this. Well, of course, what you could do, what we want here, we want to condition on the y and get the law of x given y. So what you need to do here, you need to basically get the marginal. You need to get the marginal on the y, right? And then you have to fix these y's, and then you divide by the marginal on the y to get the conditional expectation, the law of the conditional expectation. Again, it's something which is, if you try to do these things explicitly, it's impossible to grasp. It's impossible to look at it. It's impossible to say anything about this. But again, we can find an easier way. We can find an easier way to write this, and the easier way to write this is, so again, notation pi t is the conditional distribution of xt given all the observation. Yeah. Yeah.
So it should be yi minus h of xi.
Yeah, sorry. Yeah, you're right. So it's y minus h of xi because of this. Yeah. It's y minus h of xi. So this is the likelihood function. Okay. So I'm going back here, and pi t, as I said, is the conditional distribution of the signal at time t given all the observation up to the current time. Pt here is what I get after I update with my kernel, is the conditional distribution of xt given all the observation, but I'm missing the last one, right? So I go one step farther with my signal. My signal evolves, right? But I haven't yet made this next observation. So this is the prediction, the predicted conditional distribution. I'm missing the last observation, okay? And this will make the connection to the next step in the following page. So this already has only been mentioned. Qt is the prior distribution. Pi t is the posterior distribution. And now this is the recurrence formula for this, and you've heard it already twice. You've been given an exercise by Ramon for the recurrence formula. I'm not going to give it to you. I'm just going to write it in a slightly different way. So the way in which I'm going to write it, I'm going to introduce this notion of a projective product. So what is the projective product? It's an operation that takes a probability measure into a probability measure. So it's an operation that transforms from probability measure into a probability measure. And the only thing that it does, it takes the probability measure, it multiplies by a density function, by a function, right? So if I look, I can look at this as a measure here. It's not really a probability measure because I don't know if the integral over the whole space is 1, and all I do, I divide by the integral over the whole space. I normalize, and then obviously I'll get a probability measure. So the projective product is simply multiplying by a density function suitably normalized. Okay, so that's the projective product. There's an exercise here which it's a very simple exercise. Okay, so this is exactly what I'm saying in here. And then the theorem is this. So the theorem is, you've seen it already twice. To get from pi t minus 1 to pi t, I amend pi t minus 1 using my transition kernel, and then I take the projective product with the function being this gt of yt, this density function that I showed it to you on the previous page, right? So the dependence on y is here. There's no dependence on y in here at this point in time, and I'm going to come back to this because this is a very important observation. But at this point in time, there is no dependence on y in here. So the recurrence formula is like this. From pi t minus 1, I go into the amended pi t minus 1 via kt, and I denote this by pt, and then I go into pi t by taking the projective product with gt of yt. Okay, so this is a simple formula. It's misleading. You know, you can apply it, and then even if you have everything very simple, dimension 1 and very explicit, you won't get anywhere because it's a complicated, you end up with a very complicated distribution which is difficult to handle.
That's for question of multiplication. Is there any difference between left multiplication and right multiplication?
There's no difference, and I keep toggling between the two of them because I forget from one page to another which way did I put it. Okay. So now comes the theorem. So the gist of the theorem is as follows. I know the way in which pi t evolves, and if I come with an approximation, the approximation should evolve very close to the way in which pi t evolves. It's a very natural thing, right? So in what follows, I'm going to assume that I have a sequence of approximations for pi t, a sequence of approximation for pt, for any t, right? I'm not telling you that this is a particular approximation, right? I'm just saying that I have a sequence of approximation for them, and I'm going to assume that these guys are random measures. I want to cover particular approximation, but you don't have to be random. If you get something which is deterministic, that's fine, right? So I'm saying here not necessarily probability measures, but if you are not comfortable with that, then just ignore that thing. This is just simply saying that the theorem works even when you have approximating, the approximations are not necessarily probability measures, but just measures, positive but finite measures, okay? And I'm saying that none of them should be 0, so you don't work with trivial approximations, obviously. And the point I want to make is the prediction, the approximation of the prediction pt, if I integrate my likelihood function with respect to this should be positive, right? So this simply is saying that when I'm doing the projective product, at the denominator I'm going to put this value, and if this value is 0, I get nothing. So that's a theoretical, that's a technical condition that makes everything work. Okay, so if you have an approximation, a sequence of approximation, if you construct your algorithm and your sequence of approximation fits into this, then the next theorem will give you a necessary and sufficient condition for convergence. Okay? So one more notation, and that the next notation is that you construct an additional sequence which is obtained by taking the approximation for Ptn and taking the projective product with Gt. Now, I'm not saying that this one, Ptn bar, is the same as Ptn. I'm not saying that this one has to be the approximation for Ptn. And indeed, even for particle filters, it is not, right? But this is what happens. This is what I would get if instead of the approximation, I'll get Pt here. If I put Pt here, and I take the projective product with Gt, then I get pi t. So ideally, I should get this, right? Okay, so that's the notation for that. And now comes the theorem. So before I show you the theorem, here is the picture. So let's try and understand the pictures, and then you'll see that the theorem is actually very simple to prove and to apply. The theorem, so the idea is, I start with a sequence of approximation from time 0. So the point is, as n goes to infinity, I want my approximation at time 0 to converge here. Okay? So now what happens to this approximation? So these approximations are recursive, right? So suppose I arrive at time t minus 1. I get an approximation here. I get an approximation here. So this will converge, right? Because of what happened before. Okay? So what's going to happen is from here, I'll go to here, right? And then from here, I'll go to here. Okay? Now, ideally, from here, I should use my kt and go parallel to what happens to pi t, right? So to get from pi t to pt, I use my kt. I do my update. I do my kernel to get to pt. So ideally, what I should have from this approximation, I should use my kt and get to this intermediate measure, right? But it may be that my approximation, the way in which I construct my approximation is not this one, okay? And if it's not this one, the point that I'm going to make is that this difference here has to go to 0 in some sense, okay? And then what I do next, okay, so what I do next, okay, I have this perturbation. I'm going to make the constraint, I'm going to make the assumption that this difference goes to 0. And then again, I should go parallel here by using my projective product here into here I go to pi t, and here I go to this intermediate measure pi t bar n. Okay, so here this is ideally what I should have, but I may not have that, so I may have a deviation, and again I'm going to put the constraint that this goes to 0. And the theorem will so what will happen? So in the proof of the theorem, I'm going to show you the following fact: that if this guy goes to 0, so does this guy. So if I stay parallel, this guy will go to 0. So if this guy goes to 0, so does this guy. And if I want this guy to go to this guy, then this difference should go to 0. Okay? And vice versa. If I know that this guy goes to 0 and this guy goes to 0, well, if this guy goes to 0, this guy goes to 0, so this should go to 0. So the fact that this has to go to 0 is a necessary and sufficient condition. There's no way around. Okay? Right? So if you have if you have an algorithm that satisfies this picture, and if this is not satisfied, then you cannot say, oh, maybe it's still converging to 0, because this is a necessary and sufficient condition. And the next step is you do the same thing here. Now this is going to be the more difficult step, because this is a linear step. When I update my approximation of pi t or pi t itself by a kt, this is a linear transformation. Okay, so this is going to be very easy to show that if this goes to 0, this goes to 0. Here, this is a nonlinear thing, right? But still, it's continuous. In other words, if I know that this goes to 0 via my projective product, this will go to 0. So I'm going to prove that. Now, if I prove that, then what will happen is, if I know that this goes to 0, if my constraint is that this has to go to 0, and I know that this goes to 0 from the previous step, then the whole thing goes to 0. So that's the proof of the sufficiency part. And the necessary step is, I know that this goes to 0. I know that this goes to 0. Because this goes to 0, this goes to 0. Therefore, the difference goes to 0. Okay? So it's a very simple argument. Have I presented it too fast? I have. Okay. No? Anybody wants me to go over it again? No. Okay. So I'm going to now show you the conditions, and then I'm going to take you through the proofs. The proof will simply be showing you that if this goes to 0, this goes to 0, and if this goes to 0, this goes to 0, and that's enough. That does both. That's going to do both steps. So this is what the theorem says. The theorem says that if I want this convergence, so if for any measurable function this goes to 0 as n goes to infinity, and this goes to 0 as n goes to infinity, this convergence is equivalent to I have to have the convergence of time 0, and I have to have the convergence of the blue arrows. So that means I have to have that the difference between pi t n applied to the test function and this transported measure, this has to go to 0. And similarly, the difference between the actual approximation at the next step and the transported measure via the projective product has to go to 0. It's a very simple theorem. And because it's so simple, it may be worth applying it, testing it. Take your data assimilation algorithm and see if this works. See if this works. This is framework independent. I'm not telling you what n is. N is your computational effort, modeled in the way in which you like, right? Put it differently. This simply says that if I have a small error here, the error will still be small here. Sorry, if I have a small error here, the error will still be small here, and therefore what you want to keep this error small. And then if I have a small error here, the error will be small here, and then we want this error to be small. Of course, Ramon pointed out today that these errors, they accumulate in time. And that's fine. This is the next step. But at least you can have a way in which you can have some partial justification of your algorithm. So look at your algorithm and find out if these two errors are small. If those two errors are small, it means that you are in good shape. Okay, so proof. The proof is actually very simple, and I'm not going to do a lot of it. I'm just going to take you through it, and of course you'll get the slides and you can get the details of the slides. So to get to the necessary part, you have this inequality here, which is just the triangle inequality. It's just the triangle inequality. It comes from here. The difference between this and this is less than the difference between this and this plus the difference between this and this. It's as simple as that. Okay? So you know, if I know that this one goes to 0, this one is going to go to 0. And now I'm going to show you why is it that this one goes to 0. All right, so this is the linear step. So why is it that this guy goes to 0? Well, this guy goes to 0 because here's where I use my Fubini theorem, because by amending the measure is the same thing as amending the function and then applying the measure. By amending the measure is the same thing as amending the function and applying the measure. So if I look at the difference between the two amended measure applied to the test function, this is the same as the difference between the two amended the unamended functions, which I know they converge from the previous step. It's a proof by induction applied to the amended function, and I know that that goes to 0. It's really that simple. It's a linear transformation.
Yeah, this is one place where your arbitrary order between k and pi really makes a difference. Because
Yes, but I put the brackets now.
no, but in equation 11 it's very confusing. You have kt pi t minus 1f. So it looks like you apply pi t minus 1 to f, and then you apply kt to that. But that doesn't really make any sense.
Yes. So
First apply kt to pi t minus 1, and then you apply that whole measure to f, right?
yes,
Okay, so
yes. That's what I do. Yeah. So look at my picture. So I apply KT, I amend the measures, and then I take a test function and integrate with respect to the amended measure. And it's the same thing as saying I change the test function and apply the unamended measure to the change function. Okay. So that's the easiest step. And I'm now going to the projective product. This is the nonlinear step. So this is not as easy, but I have here a wonderful identity, and I know I wrote the paper on it, and then I think there are at least 1,000 papers that use this identity and get nice results. Now let's look at this identity. So this identity. So what I want to show you now, I want to show you this step. Sorry. I want to show you that if this thing goes to 0, also this step they go to 0, right? That's what I want. And this transformation is not linear. It's nonlinear because of the normalization step. Okay. Okay. So I'm writing down exactly what the transformation is, the projective product is, for each of the two things. So it looks like this. Okay? So I have PTN applied to F multiplied by the density divided by the normalization constant. And I have PT applied to F multiplied by the same density and divided by the normalization constant. Okay? So now I write it in this way. Okay? And if you have been teaching calculus to first year or second year students to prove differentiation, you recognize this. The same trick. But anyway, let me show you what I do. So what I do, I do something as follows. So I'm going to introduce an intermediate term between the two of them. I'm going to add and subtract this term. But this term is not this term, is not this term. This term inherits the numerator from here and keeps the denominator from here. So it's a mixture of the two terms. Okay? So here is where I add it, and here is where I subtract it, and I have to convince you that this is, I haven't cheated in here. So I write it in here because it's going to be very useful afterwards to get the inequalities. So look at this. So this term is this term, okay? This term is this term, and then I have this guy in here, which cancels this. So I am left with this one with a minus, and this term cancels that one. So this first part is a very awkward way to write this term with a minus. Okay, and then what's left is I have a minus, which is a plus. This will cancel this one, and I just get this term. Right, so I have a true identity here. Right? So it's a true identity. I haven't cheated here. This is an identity. Now, why is this helpful? Well, this is helpful because now I'm going to put the brackets. I'm going to say the absolute value of this is less than the absolute value of this plus the absolute value of this. Okay. So let's deal with this guy. Now, this guy here, the denominator is the same, and I put it outside. And what I have in the brackets, I have, the difference between PT and PTN, the approximation, applied to another measurable function. And I know that this is going to go to 0. I know that this is going to go to 0, right? So remember, what I want to prove is that PTN goes to PT would imply the projective product of PTN and the projective product of PT, they converge to 0. So this part is done. And then I do the same trick in here. I put the absolute value. Now, the point that is going to help me is that the absolute, this guy is a probability measure. This is coming from a probability measure, right? So the absolute value of that is less than the supremum of f. So this whole thing is less than the supremum of f, right? So this is the projective product is a probability measure. So if I integrate the test function with respect to it, then the absolute value of the integral is less than the absolute value of the test function. Okay? So I get rid of that in this way. This stays there, and what I get in is again a difference of the one that I know how to control, and this is going to go to 0. And that does it, because now I can take expectation. I know that this is go to 0, this is go to 0. These are some constants, and I get what I want. And that is my theorem. And it's an if only if statement, and it's a theorem which is framework independent. Okay? So this is a theorem which you can use to find out whether the algorithm of your choice converges, or at least it gives you good errors. Okay? So I'm not going to go through the rest. The theorem is written in details in here. The proof is written in details. I've given you enough information to be able to follow this very easily. Okay, I don't have much time left, but can I just take 3 minutes? I just want to take you through. So this is a very basic theorem, right? You can do much more than this. Okay? So what else you can do? You can compute rates of convergence, and you have here an example of how you compute rates of convergence. Not just in expectation, but you can also compute them sort of pathwise, omega by omega. So you have a way to compute, an example of how you compute rates of convergence, and you can get also almost sure convergence out. If your approximations are random,